Well, this is joint work with Arthur Dolgopolov, my former student, and my colleagues Dan Hausen and Thomas Stratman. We all have been in a situation where we are in a thin market. Thin markets are like housing markets where objects are different for different people. The job market is also a bit like that. And in these markets, to some extent, every object is a different market. In a stylized fashion, you can imagine every buyer was just one object. When you want to buy a house, you just care for one house. And in a stylized setting, you can imagine every seller has only one object. So these are called assignment markets. They are more important than looks prima facie, because housing, real estate, labor are good examples. For these kind of markets, we have a good prediction. It goes back to a classic general equilibrium paper by Shapley and Schurig. They show that for these markets, actually, the core coincides with a set of competitive equilibria and gives us the optimal assignment. Basically, the core captures the optimal assignment, the optimal way, the way that maximizes total surplus to solve these games. But the question is whether we actually can achieve efficiency in this market with different objects, bargaining possibilities, etc. So these are extremely heterogeneous situations. So this is kind of a style of representation, 3 buyers, 3 sellers. A solution for this market is assigning a buyer and a seller, but there are many ways to do that. And the point is that buyers have different valuations for the houses. So let me skip the formalities so just to give you an idea of what we do in the paper. So we set up the assignment problem. We basically take a classical Shapley-Schurig example with 3 buyers and 3 sellers. And we study the competitive equilibrium and the core that are allowed to achieve efficiency. And in the theory, we try to explore how efficiency may fail. And we propose 2 different models. One is a market game. So the idea is try to anticipate what would happen if we put buyers and sellers in a realistic situation in a scenario like that. What can go wrong? That's kind of the question that animates the theory part. And we set up a market game first, and from a market game perspective, what may go wrong is what may go wrong is that there may not, the markets may not open for every commodity in a way. So in a market game, there may be what we call semi-competitive equilibrium. These are coordination failures that may happen. From a bargaining perspective, what may happen is that some of the allocations that the bargaining game may lead to do not maximize total surplus. And in particular, we find that leximine may be an important attractor that is not captured by the core. And then we set up an experiment around this situation.
Cesar, I'm sorry. It seems like we are only seeing your title page still. And it seems increasingly that that's not right.
Yeah. How about now?
Now we see something else.
Yeah. Yeah, it's not Adobe is not working well. It's not behaving well with now. Is it passing pages?
It's we don't see the full screen. It's
full screen is not going through.
We just see the same window
with the funny things on the side and.
Yeah. But this is completely fine. So if you move forward here, we see the slides.
All right. Okay, that's crap. That.
That's better. I think you can move that window on the right in too.
Yeah, sorry about that, guys. Never. I mean, I have a funny sign on the top. Anyway, so this is the basic situation. This is the Shapley-Shubik example. So we have 3 sellers with 3 houses, 1, 2, and 3. Each seller has a reservation price. It's kind of like the cost of producing, 363 and 380. And the buyer's valuations, you can see, are heterogeneous for the different houses. And there are some gains from trade. So the matrix tells us the possible gains from trade for each possible pair. And the idea, of course, is that you can only participate in one pair. So an allocation is basically filling this matrix with zeros and ones, and every column adds up to 1, every row to 0. So that's basically. And there is a way to maximize the total surplus, and it's marked in blue. Can you see that? It's facing pages, passing pages at least. Okay, so this is the optimal assignment. And the idea is that the core allows to capture that. So I'm going to go through the details. But the idea is that the core allows to capture the optimal assignment. And the core can be decentralized via competitive prices. Basically, the prices split the surplus in the optimal allocation in such a way that given these prices, nobody has incentives to deviate and try to buy some other house. So this is a graphical illustration I like a lot. So on the left, you have the seller's payoff space. There are 3 sellers and 3 buyers. The payoff to the buyers is just the difference with what is to be split. And you can see it has a nice polyhedron shape. That's the payoff set that can be achieved in the core. And there are some points that are very good for buyers, a point that is very good for sellers. That's very typical in matching games. And on the right, here you have the competitive prices. And there is a one-to-one relationship between payoffs and prices. I like this graph a lot. It kind of illustrates what the core does. But the question is, do we get there really? And actually, can we get there using some protocol in the lab that mimics what happens in the real world? And the line question is, of course, is the competitive equilibrium a good prediction for these markets? We set up a market game. I won't explain the details, but basically the market game is like a call market, like a CLB call market. Everybody submits a bid, and then there's a clearing house, and the clearing house tries to maximize their arbitrage gains. So basically that's the idea of the market game. So what the market game does, it implements what Mas-Colell calls semi-competitive equilibria. So a semi-competitive equilibrium is basically a competitive equilibrium for a subset of markets. So market games capture the possibility of coordination failures. And that's something that we are going to keep on the back of our minds. So this is an example of a semi-competitive equilibrium. Only 2 houses are traded. So that may happen. Let's see if that happens actually in the lab. An alternative prediction to market games is generalized Nash bargaining. Of course, we are all familiar with this. Just maximize some weighted Nash product. If we do that, we may end up capturing points that do not maximize total surplus, because generalized Nash bargaining happens restricted to allocations that are constrained to transfer between pairs. So we may capture points that are not actually efficient in the simple utilitarian way. And this is one such example that is interesting. So in this allocation does not maximize total surplus. It's a complete assignment that has to happen for a Nash bargaining because, we are maximizing some, concave, concave function. And, but what it does is this allocation allows to maximize the payoff of the person who makes the least money. It's an interesting, this would never happen in presumably in a market environment because it requires some comparison of utilities, but may happens in a generalized Nash bargaining for some weights. In fact, if we have random weights, efficiency is very likely, but Lexi-mean is also somewhat likely. And so now in the experiment, we have 60 participants in 10 groups of 6. We have 15 rounds. As all this is very standard. And we use the last 10 rounds, and we implement 3 treatments. The 3 treatments are, 2 of them resemble auction environments. The last one resembles a pit trading situation, this conversation. So treatments are a minimum price. We allow sellers to post prices, and then we have buyers bidding up. If a buyer has the highest bid for a house, the buyer holds the house unless he's beaten by another buyer. So that's the minimum price environment. The second treatment is the double auction. This is our understanding of the double auction. It has to be reinterpreted for this scenario. So here we allow sellers post minimum prices, but we allow them to revise down their asks, and we allow buyers to bid up. And so that's basically what we do in the double auction. So we reduce the commitment power of the sellers. And finally, we have the pit trading. The pit trading is inspired by the traditional pit trading, but in this case, it may be useful. And we know it doesn't work so well as the double auction with homogeneous goods, but in this case, it may be useful because we have a big coordination problem. And we are not going to tell people the cost of other people, the utilities of other people. So the price discovery process here is complicated. So here we are going to allow bilateral communication between buyers and sellers, pretty free. They have a chat box, they can exchange messages, and they can make offers, and they can agree on those offers, but they can back out of them at any moment in time, negotiate another deal. So it's a bit when you buy a house, you put your word on it, you may pay a very small fee for a test, and then maybe you may back out by some other house. So until the market closes, people can back out. So that's it. And the 3 treatments kind of resemble, in a way, things we have seen, at least I have seen in the housing market. I'll skip the screens. They are kind of very standard. So this is what, for example, for the seller submits a minimum price, and sometimes the seller can revise in the double auction treatment. And for the pit trading, we have these kind of screens with possibility of exchanging messages and exchanging offers. So these are a hypothesis in a nutshell. We expect efficiency, more or less. We expect deviations from competitive equilibrium explained by coordination failures in auction environments. We expect deviation from competitive equilibrium to be explained by bargaining outcomes under pit trading. And we expect the sellers to do well when they have commitment power. And in a nutshell, this is what happens. These are the assignments and their percentage. Under minimum price and double auction, the efficient assignment is quite likely. Efficiency is much higher than these percentages. Why? Because when they don't reach the optimal assignment, they reach a second best. The second best assignment is actually a coordination failure. It's a market that doesn't open, that I showed a moment ago. And then there are other assignments that are sometimes achieved. In the pit trading, when we allow people to talk, something very different happens. First, we achieve the efficient allocation much more frequently. The efficiency gain is not so high here because the second best is very close there in terms of total utility. But something amusing happens. We achieve the Lexi mean with a lot of frequency. It's a heavy frequency, which is not something that we expect to be achieved kind of in a market environment. So that's in a nutshell what we have. So in terms of efficiency, we have higher efficiency under peak trading. The advantage is not so higher because in other cases, the second best is not that further away. And we have that, so that's basically what happens in terms of welfare. This is also welfare. Welfare is higher in the initial round. These are all 15 rounds, not everything we use for test. In the double auction, because there is a lot of price discovery within round, but the other two treatments catch up relatively fast. In terms of buyer and sellers payoff, we have sellers doing slightly better than the peak trading as we, under minimum price as we expect. And let me show the result for prices, which is just a way to illustrate what happens. So this is minimum price. Blue dots are efficient allocation. Red dots are inefficient allocation. The size of the dot indicates the number of matches. So you can see, the orange shade there is actually the core. So people are around the core, and if we magnify this, I cannot do it now. You will see the prices are kind of crawling around the incentive compatibility constraints. For the double auction, we find something similar. The blue dots are efficient allocation. The prices are around the core, covering the core around the size, which are the binding constraints. And something very different happens for peak trading. This is peak trading. So here is the core. You can see more of it now because prices are lower. Prices seem to be lower here. Like somehow evidence of buyer collusion. But we have here is actually the Lexi mean prices. So Lexi mean become an important attractor. When people can talk, we achieve more efficiency, but also we introduce somehow either bargaining consideration or interpersonal comparison. We don't know which. Summing up, we have achieved near efficiency, competitive prices. In this example, that is where actually one of the markets is marginal, allowing sellers to commit, give them more surplus. Second best Nash equilibrium and competitive equilibrium is plain auction environments with occasional coordination failures. And bargaining seems to explain deviations of peak trading from competitive. So conclusions, we can achieve near efficiency and near competitive prices, even with few participants, even with differentiated commodities and indivisibilities. Communication facilitates efficiency, but induces bargaining. That's it.
Okay, we can have a few minutes if there's any question. So we do have 3 minutes for questions.
Cesar, I have a question.
Yeah.
This is CEO. And so what's the biggest difference between the pit trading and the kind of traveling bilateral market?
Between pit trading and so what happens in pit trading is people can talk to, each buyer can talk to each of the sellers separately and exchange offers, and they communicate their intention to trade and settle for an offer. So I mean, it's inspiring in the traditional pit trading. The idea was to imagine people walking around and talking, and that is not, that's kind of very not efficient, very inefficient with homogeneous commodities where you want information to be shared and to be kind of centralized in a way or be visible to everyone. But maybe we thought useful in an environment with heterogeneous commodities. And it's kind of inspiring what we do in the housing market. We walk around and we talk. And so that's what we find is actually that. We find efficiency. Or we find more efficiency than in the double oral auction. I mean, not surprisingly, because we start with incomplete information and heterogeneous commodities, which is not the environment that the double oral auction was designed for.
Okay, it's time for our second presentation. So Philip, the floor is yours. I'll time you for 20 minutes and give you 5 minutes notice.
All right, let me try to go to full screen and make sure. Can you guys see that the slides all right?
Yeah.
Okay, so the paper title is Product Quality and Reputation in Experimental Markets. This is joint work with Mark Isaac, who's also here, and a student, Blake Dunkel, at Florida State University. So what do we do? In this paper, we conduct a market experiment with the option for sellers to send a non-binding advertisement to sellers about their product, or to buyers, excuse me, about their product quality. And as a treatment, we will prompt buyers to respond to their purchases with a 5-star rating and provide this aggregated information about reputation to the buyers, which of course is a common practice, as we all know, in online market platforms. So with this investigation, how we started out with this was we were kind of on this mission to forward a research program into the differences that we see between the results of Lynch-Miller Plot and Porter 1991, which is a classic kind of lemons market type experiment, and those found in the literature on gift exchange, which could be argued is a very similar environment in which we get these kind of very different results. So the Lynch-Miller Plot and Porter environment carries many of the same theoretical predictions as those we might find in works such as Fair and Falk, who even note that in the context of their experiments, the analogous result would have been that the sellers always choose the lowest possible effort, and the firms pay wages that are as close to the corresponding competitive equilibrium wage, right, which is this lemons market collapse. So Fair and Falk will go on to list a number of possibilities in their 2008 paper for the disparity between their own results and those of Lynch-Miller Plot and Porter. So these include the possibility for buyers to retain losses, the granularity of quality choices by the sellers, and differences between excess supply and excess demand. So in the Lynch-Miller Plot and Porter, we have excess demand, and in Fair and Falk, we have things like excess supply. So in 2008, in an AER piece, P.J. Healy performed a systematic investigation of these environments with a focus on parameter values in each environment and which ones are capable of supporting cooperative behavior, at least until the last period. And what he found was that basically this Lynch-Miller Plot and Porter environment, things about it, including especially the granularity of quality choices and the specific parameter values, is essentially a worst case scenario for sustaining these kind of folk theorem-esque cooperative outcomes that he was focused on. So for this reason, what we wanted to do was kind of build off of this LMPP environment with some more modern solutions to see what really will work and what won't, and test the degree to which these things are effective. And so to that end, I'll talk a little bit about reputation aggregation. So Lynch-Miller Plot and Porter included a treatment in which ex post revelations of actual quality were publicly announced. But they did not conduct quite very many of these sessions, but they did find a small increase in efficiency due to the treatment. And this harmonizes pretty well with papers like Bolton, Katok, and Ockenfels, in which the authors find evidence that feedback systems or reputation feedback or aggregation systems can increase efficiency, but not really to the fullest extent, which they attribute to a failure of the buyers to fully internalize the information that's provided to them through the feedback system from other buyers. So evidence shows that buyers will rely more heavily on their own experience with the seller than on that of others. And so that's one of the things that we'll be looking for. And so since we kind of want to build off of this Lynch, Miller, Platt, and Porter type lemons market environment, we design a baseline treatment to emulate treatments to emulate how real world markets have evolved to compensate for the tendency to collapse to a suboptimal competitive equilibrium. So the similarities in our design to Lynch, Miller, Platt, and Porter, we have the same number of buyers and sellers, the dichotomous product qualities, either a high quality super or a low quality regular. We have fixed types and fixed public seller identification. So sellers are assigned a letter A through F at the beginning of the session, and they maintain that identifier throughout the session. And production costs and buyer redemption values, so the supply and demand, are the same as in the original experiment, of course, with differences in the exchange rate. We aim to test the robustness of, right, this is the same. So differences, so the differences between the two. So of course, this being 30 years later, we have a number of differences that we've added to the baseline design to kind of update this in a way that will make it kind of more true to what we see in practice, and also allow us to collect a lot more data. So of course we computerized the design, which was a primary difference. It's not as pen and paper as the original. We changed the auction type to an open book posted offer rather than a standard double auction. And I will explain a little bit more about what that means later on. Of course, there are necessary subject pool differences. We are not a Caltech, we are Florida State University. That kind of is a given. So we have different subjects. We introduced a bankruptcy rule. The original authors were kind of shaky on how they describe how they deal with bankruptcies in the lab. So we kind of tried to formalize what they essentially were doing, which is we give the buyers an endowment plus at the beginning plus a per period endowment of 50 ECUs, and any buyer who ends the treatment with a negative balance will be given only their show-up fee. And then the number of periods was another thing in the original paper that was kind of a little bit shaky, but could definitely have been something that drives differences between these two environments. And that is that Lynch, Miller, Platt, and Porter, they kind of have this ambiguous endpoint where they just kind of get subjects in and tell them, you know, you're going to play these market games for, you know, until we're done collecting data, and then you're kind of free to go. So we tried to formalize that the best way we could, which is using this kind of ambiguous endpoint design, which I'll discuss in a minute. So here's our supply and demand graph. We see that, of course, we have excess demand in this market. So we call this the demand overhang supply and demand configuration. It's exactly the same as the original experiment and designed particularly to kind of induce these lemons market collapses. A little bit more into the experimental design and some of the things I talked about earlier. A market session consists of 8 buyers and 6 sellers. I'd mentioned the endowment before. They're endowed with 375 ECUs at the beginning, followed by additional per period endowment. Sellers have the opportunity to offer up to 2 goods per period. For each good, they choose a price and a quality to advertise and a quality to deliver. So there's no reason for these qualities to be the same. They can advertise something that's different than what they deliver, and of course they do. So when a good is offered by a seller, it appears to the buyers along with the price and the quality and the ID of the seller who offered it. And in order to purchase the good, buyers will type the offer number from the market screen into the box and click to accept the offer. Once it's been accepted, the seller pays the production cost for the item, which is given by the supply and demand graph, and the buyer will receive benefits according to the actual value that was offered, of course, not the advertised value. So what will we use, what will we use this experiment for? Well, our first hypothesis is kind of a replication of the original. So we want to make sure that in this new environment that we've created, reputation and brand names in a market, fixed seller identifiers in this market for experienced goods are not sufficient to guarantee efficient market operation, even in the case of repeat purchases and in this world of ambiguous endpoints. And our second hypothesis is that markets with seller feedback will be more efficient than those without. But reputation aggregation in this way will still not be sufficient to guarantee fully efficient market outcomes. And we further that to say that this will be due to a failure of buyers to properly internalize the reputation information. And our results will strongly support both of these hypotheses. In looking at the results of these sessions, we will look at the effects on two summary statistics: efficient provision, which is the proportion of offers in the session which were actually high quality, and reputation offers, which is the proportion of offers advertised as high quality which were correctly advertised as high quality. So these are truthfully advertised high quality offers, whether or not they sold. And so using a one-tailed test between the no ratings and the ratings sessions indicates a very high value, very high level of significance for efficient provision and reputation offers, indicating that both variables are significantly increased in treatment sessions. Here's a table of the average per period buyer profits for buyers and sellers in experimental currency units. At the top here, if I can. So at the top here, we'll see that we have the actual values, and then here down at the bottom, we have the competitive equilibrium values. So just to pick a couple things out on this table that you all might find interesting. We'll see that, of course, in the no ratings, the baseline, the buyers do significantly worse than both the competitive equilibrium for just a supermarket and the competitive equilibrium in a market for just regulars. So presumably this is because sellers are frequently advertising goods as supers and selling them at a very high price, which comes to the detriment of the buyers. And then another thing that's happening is that buyers will eventually stop buying goods because they keep getting ripped off, at which point the sellers stop making money. So they also don't make as much in practice as they would have in the competitive equilibrium had they just sold supers at the competitive equilibrium price or at the equilibrium price. Once we introduce ratings, the buyer profit shot up substantially, like quite a bit, a lot more than we might have even expected in a market where the only good selling was a super or a high quality good. They made a lot more than that, and the sellers really didn't change their profits at all. So the profits of the sellers remained basically constant. So those are the so those are just some things I wanted to point out here. Efficiency gains primarily driven by gains to the buyers. Even when counting only one session as an observation, the average per period profits for buyers are significantly higher across treatments, whereas for sellers, they basically don't change at all. And we'll dig a little bit deeper into that result. Here's a histogram of the number of supers delivered by a seller by treatment. So the gray bars represent the no ratings, the baseline. And we can see here on the left that this very high bar indicates almost 20 sellers across our treatments basically didn't offer any high quality goods at all ever. Whereas later on, we did have a couple of people who managed to kind of attain reputations solely through their identifiers and ended up selling high quality goods, or as many as they possibly could. And we can see that when we introduced the ratings, this flattened out substantially, and we had a lot more people up on this end who sold quite a few supers or high quality goods, presumably in order to keep their reputation high, to keep the buyers interested. Another benefit, as I said before, of our modified experimental design and computerizing all of this is that it allows us to collect a lot more data than the original design would have. So this includes the offer prices for all goods, whether or not they sold, and the ratings assigned to goods after they're purchased by the buyers. In order to kind of understand this complex interaction that we get between ratings, price, and reputation, we will conduct regression analyses on the following variables: the rating assigned to good after purchase, the price of a good offered by a seller, and the probability of that a good is purchased based on its characteristics. So beginning with the ratings. So how do buyers assign ratings to goods based on their characteristics? Well, the number one thing that we see here, so we've opted to not use, I should mention, we've opted to not use stars. So many of these things are significant, but mostly the buyer surplus value is the largest, by far the largest effect in terms of robustness, right? So what does that mean? Well, it means that buyers will raise their rating when the surplus value of their good is large. It makes a lot of sense. But it's a little bit different than what we might have expected, which is that they don't seem to really care whether or not the good was advertised truthfully, or at least that is not a significant effect relative to the amount of value that they attain from the good. So of course, there's a little bit of dependence in between whether there's surplus value and whether the good was advertised truthfully. But even still, when controlling for both things, it's kind of surprising that we don't find any effect of truthfulness on the rating that's assigned to the good by the buyer. The second effect that we notice is a strong persistence effect of ratings. So that is to say, a seller with a high overall cumulative reputation is more likely to receive a high rating on the transaction, even when holding constant the profit from the buyer. And so what's interesting is that, or another interesting feature is that truthful delivery of a high quality good is better for reputation building, even than surprising the buyer with a good that's worth more than they expected it. So falsely advertising a super as a regular and surprising the buyer with a very low priced super is actually worse for your reputation than just honestly describing what good you're providing to them. Moving on to explain the price. I will just kind of run through these tables, but please feel free to ask me to go back if you'd like to see them again in more detail. Just some highlights. The effect of a seller rating on the price is negative, which indicates even more persistence in the effect of ratings, although through a different avenue. So that is, a seller who's maintained a high rating has this perception that they have an incentive to keep this rating high by offering good prices and keeping the buyer surplus value high. We also find that ratings are not substitutes for prior notions of reputation. For example, the notion of reputation used by Lynch, Miller, Plott, and Porter, which is that sellers who have sold many high quality goods can still command significantly higher prices in the market, even when we control for the rating. Sellers do not appear to place weight on the reputation of the market, which is an important feature of Lynch, Miller, Plott, and Porter in their pricing decision. Nor do they appear to bias the price of an actual super regular differently than a regular advertised as a super, kind of to be expected. Finally, the purchase probabilities. We conducted probit and linear probability model estimations of the probability that a good advertised as a high quality will sell and a good advertised as a low quality will sell, focusing mainly on the goods that are advertised as a high quality. So not surprisingly, we find price to be the foremost point on which buyers choose to decide which goods to buy and which not to buy. Both the individual seller and the market reputations, which is the collective number of supers that have sold in the market, appear to contribute significantly to a buyer's decision of whether or not they want to continue purchasing goods. And we also find that seller rating and treatment indicator variables are not significant in, so this is kind of surprising, in determining whether or not a good advertised as high quality would sell on the market. Although of course in central tendency, they lean towards preferring sellers with high ratings. Really what's more significant is their individual seller reputation, or what we call the plot reputation, which is the number of super high quality goods that the seller has individually sold up to this point. So what this indicates is that this consistency with Bolton, Katok, and Aukenfels, which is to say It supports our hypothesis that buyers will fail to fully internalize the information offered to them by others, focusing mainly on their own personal experience with a seller when making their purchase decision. So this indicates, to kind of finish this off, a kind of paradoxical theme that is very interesting that drives efficiency improvements in this treatment. When we add the treatment, seller ratings significantly increase the efficiency of these markets, primarily through the buyer profits, right? They have almost no effect on seller profits. And this is because even though these buyers benefit the most from the addition of ratings, the efficiency gains are driven primarily by a change in behavior of the sellers and not the behavior of the buyers. In fact, it only marginally changes the behavior of the buyers and the effect is not significant. So even though, why is this paradoxical? Well, even though, the sellers seem to think that buyers are going to care a lot about their reputation, the buyers don't really seem to listen to the rating as much as they normally would have and just kind of consider how their own personal interactions have been with the seller, which should really induce the same kind of results that we see in the baseline. However, the sellers change their behavior substantially and actually make this market significantly better for the buyers. All right, and so that's all I have. Thank you very much. Happy to take any questions. No, we're not.
If no one else have question, I have one. So how would you compare your result to the one by Brown and other courses on econometric? I remember they have some results like when there is a reputation system, it can control moral hazard to some extent, and because a buyer can choose to interact with the seller repeatedly, the seller will perform better than. It will even make selfish sellers perform well, something like that.
Yeah, so I'm not actually familiar with that exact paper, but I will definitely look it up. But I can say that what we find agrees with that absolutely, completely, 100%. So if I'm understanding right, it's basically, you're saying that individual interaction with the seller is repeated over time with the treatment, right? So that was kind of our baseline. And I guess I can kind of show you, I have a couple figures here as bonuses. So this is not quite an average, but this is what a baseline treatment might look like, right? Where, just to explain this really quickly, the orange circles are goods that are actually advertised as a regular, or that are sold as actual regulars, right? And the black diamonds are goods that didn't sell. And so in this baseline treatment, even with this repeat interaction with individual sellers, and this could be driven by the excess demand because there are so many buyers and they're kind of competing over, I want this, trying to get it as fast as they can. What happens is, and this is with repeat interactions, so they know which sellers they're dealing with, and they can kind of, so what happens is, at the beginning, they just kind of buy from anybody. And then later on, we see that in this market, only one good that was a super actually sold in the entire market in the first period. And then we see that later on, people kind of figured out which sellers were trying to rip them off, and were able to kind of filter these out, which eventually collapsed the market to what is almost perfectly the competitive equilibrium for regulars, right? So with this seller identifier and with the ability to know which seller you're repeatedly interacting with, it is possible for the buyers to eventually figure out who is behaving correctly and who is trying to pull a fast one. But what we see when we introduce ratings, this kind of information overflow where, and there's a little bit more going on this, but we can see that essentially what happens is that sellers are able to more consistently maintain reputations, even starting way back in the beginning, right? So we don't have to allow this time for them to kind of to figure out what's going on and figure out which sellers to interact with, because the other people kind of will come in and do some of that work for them. So even though adding this kind of information overflow to the buyer's side, it doesn't increase the efficiency 100%. It does kind of allow buyers to have some other venue to get information from about which buyers to continue interacting with and which to just kind of stop interacting with. So I don't know if that answered your question, or hopefully not just rambling.
Yeah. Thank you. Also, this is time for our third presentation. So Brett, if you could, you can pull up your slides.
Okay, sorry, just a second. Share. All right, does that work? Let me try to make it a little larger. Fit to window. All right. Good. Awesome. All right. Yeah. So I'm Brett Williams. I'm a student at the University of California, Santa Cruz. So this is going to be a little different than, I guess, the theme of this session. I was originally in the auction session, but a time conflict happened, so I just moved here. And so my topic is going to be kind of more theory and simulations with regards to kind of minimal intelligence traders in general equilibrium settings, specifically a simple Edgeworth box setting. And kind of the flow of this talk is going to be more of a kind of a replication of a couple important models that are generally based in partial equilibrium setting, and I'll take them to a general equilibrium setting, or how I would do it. And then I'll give some general overlook on how I want to take this project further. Unfortunately, more of the data that I wanted to present kind of had the last minute inconsistencies found. So this is kind of what I've got to show. So motivation, right? Price formation has in continuous double auctions been of interest since some may say as early as Hayek in 1945, but you could say even earlier, right? With Jevons in 1862 and 1871. And the experimental work was started in 1948 by Chamberlain with a decentralized market, and then Smith in 1962 with a more centralized market. Looks like, oh, okay. Right, so for the most part, the literature has been somewhat dominated or taken front stage by partial equilibrium setting. Whether it's easier to look at, or it's just more popular, especially in early price formation models and laboratory settings. Partial equilibrium has really taken the front stage. And kind of despite how relevant general equilibrium is in both modern microeconomic theory, analysis of financial markets, and as far away from experimental as macroeconomics, we find that price formation and trader behavior in general equilibrium settings is holding a relatively smaller portion of the literature. So I'd like to kind of expand on that. Right, so a little bit of literature. Obviously, there's a lot more than this. So this is why I say just a selection. These are kind of the papers that my project most closely relates to. right? So one of the kind of most famous minimal intelligence or zero intelligence models is Golden-Sunder 1993. And then there are expansions or kind of question papers about zero intelligence, right? Such as Cliff and Bruton 1997 with their Zero Intelligence Plus. Golden-Sunder check their budget constraint, just as Jerstead and Shackett does, and Cliff and Bruton as well. And then if you want to go to higher intelligence, earlier price formation models that are also in partial equilibrium, you have stuff as early as Wilson in 1986 and Friedman in 1991, all the way up until a couple of relatively recent changes with much more complex, much more intelligent traders, such as Onufriev et al. 2013, where they're using their individual evolutionary learning, and Van der Loer and Onufriev, which add a timing element on top of this as well. The general equilibrium DA models that I'll kind of refer to, the first and last paper here are actually not models, they're experiments. On the modeling side, there's relatively few that are directly related to kind of the simpler Edgeworth box setting that I'm thinking of. But Golden-Sunder make an attempt at this in 2004. However, they kind of stick to just single unit trading. And then Crockett, Spear, and Sunder take a more advanced attempt at this. So what I'll be doing today is looking at kind of two of these models, namely Golden-Sunder 1993, the original Zero Intelligence paper, and then Gierstedt and Dickup 1998, which is a paper that uses kind of a belief-based or a belief-driven setting to get their price formation or price dynamics. So trying to position this project kind of how I just mentioned, right? The literature is decades old, right? Potentially 150 years old if you want to start it at Jevons, and spans across theoretical, experimental, computational works. Most of the time these papers combine all three, and it occurs in both partial and general equilibrium. However, like I mentioned, partial is going to be taking the front seat, especially in the modeling subliterature. So this leads me to believe that there's potentially some room for an expansion in the general equilibrium side, especially with going slightly more than zero intelligence, right? Minimal intelligence, I guess. So the idea there is then advancements in this modeling literature could then propel more investigation into lab markets and general equilibrium settings as well, which are somewhat more complex for the subjects to see. And as we've known, a lot of the laboratory markets have subjects participating in partial equilibrium settings where generally what we see is they converge, right, to predictions. But general equilibrium settings, depending on kind of what utility functions you give the subjects and so on, it makes things much more difficult. So I think that'd be interesting to look at. And so the goal here is to try to replicate a couple important stages of intelligence and trader behavior in a really simple Edgeworth box setting, just two goods, two consumers, no production, and provide a new model, hopefully on price formation that expands on both belief-driven models as well as hopefully capture the convergence seen in labs, but also some disequilibrium activity you see in labs. Right, subjects taking trades that they shouldn't be taking, and so on. So starting with the environment or explaining that a little bit more, right, I'll be looking at a two good, two consumer pure exchange economy. Good X is going to have price X, and good Y is going to act as a numeraire. We'll use CES utility functions. One nice thing about CES is if you vary the parameters throughout, especially R, right, you can go as high as R equals 1, which is essentially just linear indifference curves. 0 is going to approach Cobb-Douglas, and then as far as negative infinity is approaching Leontief. So there's a nice range there where you can really get different levels of curvature in your indifference curves. And so that's going to kind of manipulate what contract curves look like, how much space these subjects have to move around. Traders participate as two-way traders instead of the usual specialized buyers and sellers, right? So they can operate on both sides of the market. And their parameter sets and initial endowments are going to be what pushes them initially as either natural buyers or natural sellers. It came back to the good side. Okay. So traders are going to participate in a continuous double auction in this environment where bids and asks are going to be placed at any given time. There will be an order book available. Some of the literature only allows for the best bid and best offer, but I'll have the full order book available. Transactions can occur when either accepting or crossing an existing order, and traders are going to participate in as many transactions as they wish, right? So they're just your standard continuous double auction, right? So the first kind of level of intelligence that I'm going to try to take from partial to general, which has been done a few times, this is just my take on it, is zero intelligence, but in a Edgeworth box, right? So in its original partial equilibrium form, zero intelligence framework has a spread reduction rule, which basically just means you have to submit a bid that's better than the best current bid in the market or a better ask than what the best current ask in the market. And that is the only bid or ask in the book. There's a budget constraint, which is the referred to commonly as a zero intelligence constraint version, which is going to act as a no loss constraint in partial equilibrium, right? Buyers cannot submit something that is higher than the redemption value, and sellers cannot submit something lower than their cost, right? In a general equilibrium form, as Kierstead and Shackett kind of say, is this is going to act as a utility floor, which can be very influential to traders. I need to stop pressing that portion. Let's see. Okay. Trader behavior is going to be defined as follows. So traders enter randomly, and buyers get to make a draw from 0 to the redemption value with a uniform distribution over it, and sellers make a draw from a uniform distribution over their cost to some maximum value that's imposed. So changes that need to be made or that can be made to ZI to help bring it to general equilibrium. And what I'll be doing is allowing buyers to make a uniform draw from 0 to the highest price that still yields at least the same level of utility, right? So as their current bundle, and sellers a uniform draw from their lowest right utility maintaining price to some maximum, the same maximum that you would impose on these zero intelligence and partial equilibrium. And then buyers and sellers are not given redemption values or unit cost lists, right, schedules. They'll use this budget constraint or utility floor to kind of push them along. Additionally, kind of following these adjustments, I decided to make it a little bit more general and less restrictive. So traders can both buy and sell, so they're two-way traders. And the side of the market they enter on is going to be decided by a weighted coin flip, where that coin is weighted by basically the size of the region on either side of the market that they can enter. Kind of analogous to, you know, which side do they think they'll be able to take more advantage of. And then orders may be in multiple units in size, and units are divisible, right? So instead of just the classic single unit. So I've run a batch of 100 simulations. Luckily, I was able to get this set of simulations debugged. So I set buyer parameters and seller parameters. You'll notice R is set to 0.5, so somewhere between Cobb-Douglas and linear. And buyers are going to start with 1 unit of X and 22 units of the numeraire. And sellers are going to begin with 10 units of X and 3 units of the numeraire. And the general equilibrium price in this market is 2.65. Traders are going to have multi are going to be two-way traders, and it's going to be multi and divisible unit. And what we find is that the final price, average final price, is about 13 units away, 0.13 units away. And the final competitive equilibrium price, after taking into account the potential for some of these trades being disequilibrium trades and moving the competitive equilibrium, it still remains relatively close at 2.67. The final spread center is a little shy of the general equilibrium price. And you'll notice that the deviation from the general equilibrium price, the absolute deviation, is about 0.55. So as in the partial equilibrium version of ZI, it bounces around quite a bit, but it seems to center around decently well to the general equilibrium prediction. Then moving on to the kind of second stage or second level of intelligence that I'm trying to incorporate is this belief system that Gerstedt and Dickout in 1998 incorporated, where basically they have another partial equilibrium setting, also with cost and redemption value schedules, and traders, thank you, attempt to maximize their surplus, placing orders using beliefs on the acceptability of each price. So the traders basically maintain a limited memory, and they're going to look over all the prices within that memory and find out basically the probability that each of those is going to be accepted. So they do that by totaling the number of successful asks and bids at prices higher than that, and then dividing that by those total number of successful orders plus the number rejected at prices lower. And buyers will do something analogous to this, just the flip side of it. And traders are then going to find the expected surplus for every one of these prices and choose the highest expected surplus as their kind of chosen price. They'll draw from a uniform distribution around this price that's going to be bounded by the nearest prices on either side. The other important part of this model by Gerstedt and Dickout is the timing of submission. So after every price is submitted or transacted, essentially they're going to reevaluate their memory, or update their memory and reevaluate all of their expected surpluses. And then these surpluses are going to be weighted by how much time is left in the period to kind of either slow them or make them try to get into the market faster. And the person with the least amount of time they're willing to wait is going to enter in the market next round. Right, so I've also run simulations for this in general equilibrium. It turns out if you allow the units to still be single instead of multiple or divisible, the model translates really well to general equilibrium as far as not having to change too much. The only thing really needed to allow it to run is one assumption on the very first period of how the traders think about how they're going to enter. So basically they're going to have kind of monotonically decreasing or monotonically increasing, depending on whether buyers or sellers, choice over their kind of range of what prices they can take. So for buyers, it's going to be 0 all the way up to that M we talked about in zero intelligence, and sellers, it's going to be the reverse. And what I found here is actually, it doesn't, while it translates in terms of ease of use, it does not really translate in terms of successive reaching price, right? So it's a bit further away in final price, average final price. The absolute mean deviation is slightly larger. And the final competitive equilibrium price is a bit further away from the original competitive equilibrium, meaning there was larger or more disequilibrium trades. So the new model moving forward that I'm trying to instill is going to have this same type of belief-based price choice process, also in a pure exchange economy, but have two-way traders instead of specialized buyers and sellers, multiple divisible unit orders, an order book that is not necessarily subject to a spread reduction rule. So you can post to an order book without having it be the highest price or the highest bid or the lowest ask. potentially you're trying to position yourself, or right, the prices are too aggressive for you, so you might want to wait, but you want to get your order in earlier. And the possibility for error with regards to a utility floor rule, right? So possibly placing something that is below your current indifference curve, or accepting something there, right? Which we do see in general equilibrium, thank you, experiments, right? So the last kind of thing I'll say, the last slide I'll go through, is just that I intend to use reservation prices, where the traders have a reservation price on either side of the market, and they're basically going to look at all feasible price vectors extending from their current bundle. And along each of these price vectors, they'll look at each potential bundle they can move to and compare the utility gained for this relative to what they would get by moving that same amount along the reservation prices. And they'll find the expected utility gain on either side of the market, and basically compare theirs to the total of the rest of the market, which will be their probability of entering into the market on either the buy or the sell side. And then once they're in, they'll apply logit probabilities over each potential order, price and quantity, where essentially the lambda you see here is going to range from extremely high values of lambda, which is basically going to look like the Kierstead-Dickau beliefs, or an extremely low lambda, which will basically move down to ZI type behavior. Thank you for your time. I think I hopefully didn't go over. Any questions are welcome, and thanks again.
I have a question. If we have
yeah.
Yeah. So it seems like essentially what you've done is merge these two separate but similar literatures on beliefs and price formation into, you know, this kind of model that sort of splits the difference, right? Where it's parameterized by this lambda. So it would be interesting, I guess, I don't know how much this is a comment or a question. It'd be interesting to see an estimation of that on some real world data, be it either, you know, an experiment or even an application like a structural estimation. If you, I was just wondering if you have some kind of.
Yeah, I intend to run experiments to kind of test this, and then as you mentioned, you know, having real world data would be amazing as well. But I fully intend to run some lab experiments where subjects participate in this. There's at the LEAPS lab, there's some software under the works right now, so hopefully soon I'll be able to run those. But yeah,
cool. Forward to it.
Okay. So I'll start presenting my paper, and this is a joint work with the first presenter, Cesar Martinelli, and also Jianxin Wang. And in this paper, we studied competition with indivisibilities and field traders. So let me motivate our paper with the contrasting ideas in this page. So from our textbook view, a very standard view for competitive economy, the requirement is that there are many buyers and many sellers in the market. So each person will have a negligible effect on the price, and everyone can act as a price taker. And in this setting, we do require a lot of buyers and sellers in the market to reach a competitive outcome. And indeed, this is a competition in a Coulomb way. So there is only one price in the market, and buyers and sellers choose the quantity they are willing to trade at. But there is another strand of thought and result, and which is also what this paper is more agrees more on, is the result from laboratory experiment on double auction and also the theory of Bertrand competition. So in double auction experiment, what we have seen is that with very few traders, like only 4 buyers and 4 sellers in a market, the price converges to competitive level very quickly, and also the efficiency in markets are high. And also in the Bertrand competition sense, which is similar to double auction, that people post prices they are willing to trade at. When there is a price competition, we need only 2 sellers to reach a competitive outcome. And in this paper, we show a theory that's in line with the competition doesn't require a lot of traders view. And also we tested in a laboratory experiment. So what we study here is under what conditions do competitive equilibrium emerge? And what we propose is a market game. So in market games by Dubé, Simon, and Bennessy, where there are buyers and sellers in a market, and each trader proposes a price and quantity to the clearinghouse. With their mechanism, the result they have is that when there are 2 active traders on each side of the market, then the Nash equilibrium outcome is competitive. And in this paper, we are going to expand their result to an indivisible good environment. And we obtain a sufficient and necessary condition for the coincidence of Nash equilibrium and competitive equilibrium. And what we do next is we test it in laboratory experiment. And so previously, Friedman and Ostroy had tested the theory from Dubé, Simon, and Bennessy in laboratory experiment. What they find is that with 3 or 4 traders on each side and with divisible good, there is a convergence to competitive outcome. And what they adopt in the experiment is that although traders know only their own reservation value, but with the information they can obtain from the market, the result is similar. The result is close to what Nash equilibrium predicts, as if there is complete information in the market. And in our experiment, we are going to test the same thing with our mechanism as well. So in this paper, theoretically, we extend the Dubé, Simon, and Bennessy's result to indivisible commodity environment, and we obtain a condition for the equivalence of competitive equilibrium and Nash equilibrium. And in experiment, we are going to test it and compare the performance of our mechanism with the performance of double auction. So the economy we use here is the same as the one from Friedman and Ostroy paper, and this is a very regular economy in double auction. So we have 2 goods. One is an indivisible good, and we have money that people use to trade, and money is divisible here. An agent in our economy is either a buyer or a seller, and each agent has reservation values for multiple units. Buyers has decreasing marginal values for the good, and sellers has increasing marginal cost. And the payoff for buyers and sellers are also the same as what happened in double auction. For a buyer, the payoff depends on the quantity he buys and the money holding. So the buyer gets utility from the money he holds and also whatever values he has from the good. And for a seller, his payoff is the money holding minus the cost incurred if he sells the good. So let me show it in a graphical way. So this is also the setting we're going to use in our experiment. We have 2 buyers, buyer 1 and buyer 2 in the economy, and 2 sellers. And each person has 2 units of a good they want to buy or sell. And with this is the reservation values the buyers and sellers have. So this forms the demand and supply curve, and this range is the competitive equilibrium price range. The mechanism we propose is a Bertrand-style clearinghouse. So what happens here is that every agent submits a sealed bid to the clearinghouse. And in that sealed bid, the agent needs to specify the price he's willing to trade every unit at, and the maximum quantity he's willing to trade. And if the agent make any transaction, the price will be whatever he will trade at the price he offers. And all trades are voluntary, so no one sells or buys more than what they proposed. And the main part is how the clearinghouse decides trade. So here our clearinghouse will choose trade to maximize its own profit. So it will act as an intermediary and buys from the sellers and sell it to the buyers. So here's what the buyers and sellers proposed to submit it to the clearinghouse. The clearinghouse will rank all the bids the buyer submit from high to low to form a pseudo demand curve, and rank all the asks from low to high to form a pseudo supply. And as an intermediary, the clearinghouse will execute the transactions on this part so it can make profit out of it. And we also make the clearinghouse execute as many transactions as possible. So in this case, the clearinghouse will buy from all sellers to the left of this point and sell it to the buyers on the left of this point. And in case of tie, a random draw will happen between these two, and one of the sellers trade the good. So how would a Nash equilibrium look like in this mechanism? Firstly, we can show that all active traders in this mechanism will offer the same price. Here by active, we mean that the person has a chance to trade in that Nash equilibrium. And then we can show that whatever competitive equilibrium it is, we can find a Nash equilibrium that induces the same outcome with probability 1. And another result, that's another important property of the Nash equilibrium, is that if there are at least 2 active traders on each side, then we can show that every positive probability outcome is competitive. So with this, we can reach to our main theorem. So here we propose a necessary and sufficient condition for the coincidence of Nash equilibrium and competitive equilibrium. Basically, we say that if there are at least 2 inframarginal traders on one side and at least 2 weakly inframarginal traders on the other side, then we know that all the outcomes from Nash equilibrium is competitive. So what is a inframarginal trader here? So this definition is quite relaxed. So it depends on the competitive equilibrium prices. So firstly, we find the lowest reservation value that can trade in every competitive, that the buyer can buy at every competitive price, and the highest reservation value the seller sells at every competitive price. If a seller is inframarginal, what we mean is that the seller is willing to sell at every competitive price. The seller has a value lower than VS, low or equal to that. And the weakly inframarginal seller, the definition includes the inframarginal seller. So if a seller is weakly inframarginal, the seller generates positive social surplus if he trades with an inframarginal buyer. And what we can see in this economy is that both seller 1 and seller 2 are inframarginal because both of them has a unit values that no higher than Vs. And we have two inframarginal bias here, buyer 1 and buyer 2. So what is predicted by that, what is said by our theorem is that in this economy, all the Nash equilibrium outcome will be competitive. And that is what happened on the left panel. And on the right panel, we can see that there is only one inframarginal seller here. Only seller 1 is inframarginal. Seller 2 doesn't have a reservation value lower than Vs. And what we can say with this economy is that for the economy on our right-hand side, there are some Nash equilibrium that has price higher than competitive level, and people trade less than efficient. But there are also Nash equilibrium that has the competitive outcome. And in our laboratory experiment, we are going to compare the outcome from these two environments. So what we do in our experiment is that we have exactly the setting we saw before. We have 2 buyers and 2 sellers in the economy. And each buyer buys up to 2 units and each seller sells up to 2 units. And the buyer's payoff is the difference between the value they obtain and the payment they made. And seller's payoff is the difference between payments they receive and the cost incurred. It's very standard double auction setting. And here, since we are studying whether people can obtain enough information to reach the Nash equilibrium outcome, we have our groups and reservation values fixed to help learning. And here in our experiment, we push the theory to one step forward. We give people a private information on values, same as other double auction settings. So what had been found in literature is that in double auction, although people didn't have the reservation value information of other traders, at the end, the Nash equilibrium, the outcome is still, at the end, they reach to an outcome as if they have the complete information. And this is also the Hayek hypothesis, that the system generates enough information to reach competitive outcome. And here we are going to compare the competitive environment and the environment where there is a monopoly, as I shown before. And also we will use double auction as our benchmark to compare the result of our clearinghouse with. And indeed, the mechanism we propose here is actually a static version of double auction. So the main hypothesis we have is that under both institutions, when the market is competitive, we observe lower price and higher efficiency than the monopoly market. And the other hypothesis is that since double auction allows more information flow than our sealed bid mechanism, there may be higher efficiency under it. And we ran our experiment at George Mason University and with 240 subjects. And this is what we found for the efficiency. And there are 4 lines here. This is efficiency as the percentage of social surplus achieved, the percentage of social surplus achieved, and over time. And the red lines are the result from double auction, and the blue lines are the result from our mechanism. The dashed ones are for the monopolistic market. So what we can see here is that under double auction mechanism, the efficiency is high from the very beginning. And with the clearinghouse mechanism, as people learn, the efficiency goes higher gradually. And at the end, the levels are similar. And the other result we can see from here is that when the market is monopolistic, which is on the dashed line, we can see that double auction also allows more learning for the monopoly, and the monopoly are able to extract more monopolistic power. We will see better in the next graph with the price. But with the clearinghouse mechanism, there is no much difference between the market when the market is monopolistic. And here, if we check the price, it gives us similar information. Under double auction mechanism, the monopolistic market has an effect on the price, but the effect is not so obvious using the static mechanism. And what we also see here is that the price goes into the competitive range from the beginning in the double auction mechanism, but it takes longer for people to learn in the clearinghouse mechanism. And another thing we tested here is the long run trend of the price. So what we can show is that in the long run, the trading price is within the competitive range. If for these three treatments, for the clearinghouse treatment and for the double auction treatment under competitive market. But if the mechanism in use is double auction and the market is monopolistic, the long run trading price will go beyond the competitive range. So the main information the main takeaway from this study is that in spite there are very few traders, both the institutions in comparison show convergence to the competitive outcome, and especially in the competitive market. And trades are closer to equilibrium, and as if agents have full information, like predicted in Nash equilibrium. And both the clearinghouse mechanism and double auction allows participants to learn enough to reach the equilibrium outcome. And as we guessed, the participants learn faster in double auction. And another main takeaway is that under the double auction mechanism, the trading prices are higher when the markets get monopolistic. So that's all we have. And yeah, I think I'm good on time, and we have 5 minutes for questions.
I have a question.
Yeah.
On the monopolistic, you did a monopolistic a little fast. Is it bilateral monopoly, or is it just the seller only?
No, it's only one side. We only tested when in this environment, when there is a monopoly.
Okay, yeah, one seller, yeah, but the buyers are competitive.
Yeah,
okay.
The buyers are competitive, yes.
If anyone else has a question, they should go ahead, but I have a second question.
Yeah.
Don't see any other hands. So, have you had a chance to look at the individual behavior? This, in the theory, at least the way Joe Ostroy and I put it together, we thought about this in terms of under-revelation in either the price dimension or quantity dimension. The institution you have is different than the one we have, but it would seem it had very strong incentives to under-reveal in price dimension, since you have to pay your own price if you're bidding, or you only receive your ask price if you're asking. You'd like to under-reveal your willingness to pay. In other words, you'd like to bid lower than your reservation value and ask higher than your cost, because that's the only way you can make money. So it's very strong incentive.
Yes.
Did you compare people also under-reveal in double auction and in uniform price settings? Did you have a chance in your paper to compare the degree of under-revelation in the price dimension?
So theoretically, in the Nash equilibrium, people will under-reveal or over-reveal. And what we show is that this not truth-telling didn't have, we still reach full efficiency with this without truth-telling, because this is in a Nash equilibrium setting. And
in equilibrium, yes.
Yeah, in equilibrium, yes. So that doesn't harm efficiency. And what we see in the, we have buyer-seller payoff. So that's actually the amount of under revision they have. And
well, but the under revelation would also occur when they don't transact, right? So they could get a payoff of 0 because they under revealed too much relative to what everyone else is doing.
Yes, that's also what happens in the clearinghouse mechanism. And we saw that it's kind of a bargaining process. So, and that's like people were under revealing and then keep trying to move towards the center or towards the middle and or reach a point that they can agree on. And that's a reason we think why the clearinghouse mechanism didn't have as high efficiency as a double auction, because the cost of under revealing is higher.
Mm-hmm.
Yeah, but we did observe some of those, yes.
Okay, thanks.
Just to carry on Dan's question, you could actually, I think this is what he's saying, just actually like graph out some kind of average revelation curve in the clearinghouse markets, right? To get an idea of where misrevelation occurred. Is it stronger in the inframarginal units than the ones closer to the equilibrium, and so forth.
Yeah, that would be nice. Yes. Yeah, we had a graph like individual bids and ask, and it's very much like what we normally observe in double auction, that people keep bargaining and the bids and ask moves towards each other over time. And that's the same in the clearinghouse mechanism as well. But thank you for that suggestion. Yes.
I think that's a really interesting result. You're saying that across periods.
Yes. They are learning across periods, but what we have here is fixed group and fixed value.
Well, in other words, a famous case in the 1970s where because of a legal standpoint, they had to collapse a lot of the treasury auctions that would ordinarily occur across several months into about 3 days. And so it was like you were repeating very much the same conditions because there wasn't that much new news coming in, but they were doing it over and over, and you saw these flattening of the revealed curves. So by the third day, they were very, very flat on the inframarginal side, which sounds like a quite similar phenomenon to what you're finding in your markets. So I think that's really interesting.
Thank you. And I think we are out of time. So thank you very much for attending this session.